Alrighty, guys, welcome. I know that link just got posted, so it'll probably be a second as folks filter in. My 11 o'clock class has a tendency to run a little bit over, so I'm sure we can pitch me there. Last time we talked about average rates of change, and we stopped just short of asking and answering a very interesting question relating increasing and decreasing to average rates of change being positive or negative. Today, we're going to ask and answer that question in detail, and then we're going to talk about transformations of graphs. We may not get all the way through the transformation section. That's okay if we don't. We'll continue it on Tuesday if necessary. All right, here we go. This is MAC1140, section 009, which is a class. Today is the 9th of September, 2021. And as long as we will finish section 2.4 on average rates of change. And then we're going to talk about section 2.6, which is transformations of graphs. Okay. You notice we're skipping over section 2.5. 2.5 in your textbook is on linear models, like using linear functions to model real world things. If you took college algebra here at Santa Fe, then you got plenty of that shit. It's something that you've seen since 8th grade. We're not gonna tread over that again. But there was this question at the end of the average rates of change section that, that we were sort of leaning into, but didn't get to fully explore. So I want to begin with that. And so let me first say recall that the average rate of change, for abbreviating AROC, average rate of change for the function f from x equals a to x equals b is f of b minus f of a divided by b minus a. And that numerator is something we had seen before. That's the net change. And the thing downstairs is the length of the interval a to b. So kind of remember, net change is how much your function has gone up or down overall, right? How high did you end up compared to where you started? So what we're doing here is asking, like, how much did you really change divided by how long did it take you to do that change? The examples we saw were like a change in distance over a change in time is a speed, right? It's like net change in distance divided by the amount of time it took to get that net change was your average speed or your average velocity. Geometrically, this was like, okay, if I've got my function f and I've got some points, 2 points on that graph, a comma f of a is over here, b comma f of b is over there, then the average rate of change was the slope of this secant line, the line that connects those points. Which isn't the slope of the function. That function is all curvy and shit. It doesn't have a fixed slope. But that blue dotted line that we get by just connecting the 2 points on the graph, that secant line, is a line. So it does have a slope. All right. Before I ask you the question, I want to share with you a fact. It's a fact in 2 acts. The first act says, if f is increasing on the interval a, b, perhaps elsewhere, but at least on that interval a to b, maybe something like this. So a is over here, b is over here. If your function f is increasing everywhere along the interval a, b, perhaps elsewhere, but at least along that interval a to b, then the average rate of change from a to b has to be positive. The average rate of change from x equals a to x equals b must be positive. Can't escape it. If the function is increasing everywhere on the interval a, b, that means every time you take any sort of step over to the right, you're also taking a step up. So as we go all the way over to the right, we're going up that whole time. That means this guy has to be higher than this guy, which means the net change must be positive. Hence, the average rate of change is positive as well. The other side of this coin is if f is decreasing everywhere on the open interval from a to b, picture looking like this perhaps. A over here, b over here, b comma f of b there, a comma f of a there. Then the average rate of change is the slope of that secant line, which is necessarily a negative slope. So the average rate of change from x equals a to x equals b must be negative. All right, now here's the question. Is the converse true? Converse is not just a sneaker brand. It has a very specific meaning in mathematics and logic. The converse of A implies B is B implies A. So increasing implies positive average rate of change. Does positive average rate of change imply increasing? Is it the case that if the average rate of change for f from x equals a to x equals b is positive, that f must be increasing on the interval AB. And you can change positive to negative and increasing to decreasing. Same question. So what do we think about this? Here we see increasing function, positive average rate of change. Could you deduce from the positive blue slope here that the function has to be increasing? Is it possible to have a positive blue slope but have the function be decreasing ever?
I'd say it's possible, but like within the points, it'll always be what it said. Like outside of the points, it could later on curve again and start.
So I like what Gavin is doing there. What you're doing is very important. It's like poking at the hypotheses of the question. we are saying strictly between the points. So strictly between the points, is it possible to have a positive blue slope, but not always be increasing between those 2 points? Yeah, certainly outside here, this function could turn around and come down, right? But what about inside here? Could it go down in here ever and still have a positive blue slope?
No.
Feeling is no, right? Let me bring this back. This function from A to B, I think we would all agree, has a negative average rate of change, right? This point is a little bit below this point. But we're increasing, 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 decreasing, 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 increasing, increasing, increasing. We've got both behaviors. So kind of, in a way, it has to do with how far apart these points are. And you're going to investigate that very carefully in Calc 1. The answer to this question is a negative. It is possible for f to have a positive average rate of change, but not always be increasing on AB. And the average rate of change is from A to B, right? Now there is more to this, and we're going to look at this a little bit deeper. If you require that the function be continuous, which is a word we haven't used much, but means the graph is connected, you can draw the graph without lifting your pen. If the function is continuous, at least on the interval A to B, then it's true that the function has to spend some time increasing in order to have a positive average rate of change. But it's not true that it must spend all of its time increasing. And to further drive this home, let me show you a few counterexamples. Okay, so we want a positive average rate of change, but not necessarily increasing the whole time. Here we go. This function has a positive average rate of change from A to B. But we're decreasing up to here and increasing from here on. So it's possible to have a positive average rate of change, but not always be increasing between A and B. Now, what is true is that you have to increase more than you decreased, right? From A to B, we decreased by this much and then increased by this much. It can get worse if you allow the function to be discontinuous. So for example, I could have a function like this. The actual point on the graph at x equals b is the filled in point, the solid point over there. We saw this when we talked about piecewise functions. This function is decreasing pretty much all the time, but it still has a positive average rate of change. If this tickles your brain in a pleasing way, you should study analysis. Analysts spend their time asking questions like this. Is the converse true? How can we fuck up this intuitive thing that seems perfect? How can we take something that seems to make wonderful sense and satisfies our intuitions beautifully and then go, how do I break it? That is the mind of an analyst. That is the mind of Walter Rudin or Paul Halmosh or I don't know, take your favorite analyst. So yeah, not necessarily, although it seems like it should be true. It's not necessarily true. If you require the function to be continuous, then there is a slightly weaker statement which is true, which is that the function has to have increased more than it decreased to have a positive rate of change. But if you break the continuity, then you can do weird stuff like this function, which is decreasing from pretty much everywhere. All right, it's decreasing here. It's decreasing here. The only place it's not decreasing is somehow right there at that point. But still a positive average rate of change. All right, so the folks who invented or discovered, depending on your perspective, calculus are people who thought very hard about these sort of things. Newton and Leibniz would have understood this. They would have been a little surprised by this. And then people like Cauchy and Weierstrass started looking at things like this. Okay, so not necessarily, but good question. That's the end of section 2.4. So the book actually just tells you this, just tells you this stuff. They don't ask you about this stuff, but I want you thinking about that stuff. It's the way you strengthen your brain. We're going to begin now section 2.6. The big idea is if you know the graphs of the basic parent functions, which I'll remind you on Tuesday I showed you in Desmos, there's a link in the modules. We can use those to get graphs of lots and lots of other functions. Basically, what we're going to do is we're going to take those basic graphs, the graphs of parent functions, and slide them around, left, right, up, down. We'll flip them over, we'll stretch them out, we'll shrink them in. And that will give us a big infinite family of functions that we can graph. Anything that's based on one of those parent functions, we will be able to sketch quickly without making a table, without plotting points, just by transforming a known graph. You got to know the parent functions. This is step 0. You have to know these guys. Where are these guys? They're here. Sorry, not there. They're in the modules. Here. Right? Click that link. Here are your basic parent functions. And each one of these is like a family that you can see how to extend, right? The next one in this first family, x squared, x cubed, x to the 4, x to the 5 would be x to the 6. And there are patterns here. Here's x squared, right? X squared is that parabola that we all know and love. Here's x cubed. Oh my goodness, thank you, baby. My wife just brought me some awesome coffee, which is great. I need that desperately. X squared, x cubed. Here's x to the 4. Looking an awful lot like x squared, just a little bit flatter on the bottom, right? It's kind of like someone took x squared and went, pushed it down. X to the 5, looking a lot like x cubed, but again, just a little bit flatter around the origin. Y equals x to the 6, looks a lot like x to the 4th and x squared. You get the idea. So these you need to know. Also, Here's the square root of x. Here's the fourth root of x. Here's the cube root of x and the fifth root of x. And then your reciprocal or negative power functions, 1 over x. Let me zoom out a bit. 1 over x is this blue graph. 1 over x cubed looking a lot like 1 over x, just sitting down a little harder on the x-axis. 1 over x to the 5 looking a lot like 1 over x cubed, just sitting down a little harder on that x-axis. And the even powers, 1 over x squared, 1 over x to the 4. Very similar to each other. And the last one I've included in this list is the absolute value. So you must know the graphs of these functions by heart. Should be able to ask you, what does x to the 5 look like? And you sketch it. It goes, and there it is. All right. So step 0 for this section, which is section 2.6. Know your parent functions. Gotta know those guys. Now, once you have those guys tucked neatly into your pocket, you can move them around to get lots of other graphs. Like I said, you can flip them over, stretch them out, compress them in, drag them left, right, up or down. And that's what I'm going to show you how to do today. The examples I'm going to use today, I'll try to keep the parent functions fairly simple because I'm not sure how well you all know those, but you got to learn them, right? You will be dead in the water. There will be a 10-point question on test 1 that asks you to sketch the graph of a parent function, apply a set of transformations, and sketch the graph of the resulting function. And if you don't know what that parent function looks like, you're dead in the water. So please study those Desmos graphs. If you need to, make little flashcards, all right? Print them out, make little flashcards. Who's that, hazelnut? It's very nice. Oh, is that a sweater for Dan? Oh. All right, sorry. All right, so here's how I'm going to introduce the transformation stuff. I'm going to give you a transform function. We're going to graph that transform function by plotting points, by making a table. Then we're going to compare that to a parent function and realize how we could have done it without making the table. And then we'll do an example that's similar just by using the transformation. At the very end, I'll give you all the transformation rules. All right, let's sketch a graph of f of x equals x plus 2 all squared by plotting points. So we're back in 8th grade. We're going to make a table. Our table is x values and y values, or x and f of x. And for my x values, I'll use like -4, -3, -2, -1, 0, and 1 for reasons that will become clear. If I plug in -4 for x here, I have -4 plus 2 all squared. -4 plus 2 is -2. -2 squared is +4. If I plug in -3 for x here, then this is -3 plus 2 all squared. -3 plus 2 is -1. -1 squared is +1. If I plug in -2 for x here, then this is -2 plus 2, which is 0 all squared. 0 squared is 0. If I plug in -1 for x, this is -1 plus 2, which is +1 all squared. So that's 1. If I plug in 0 for x, I get 0 plus 2 all squared. That's 2 squared, which is 4. And if I plug in 1 for x, I get 1 plus 2, which is 3 squared, is 9. So each row here tells me an ordered pair on the graph of f, right? -4, 4, -3, 1, -2, 0. I'll call this -4, which makes this -2. That's -1. That's -3. This +4 here. Maybe I won't plot this last one. That's okay. All right. So -4, 4 is on the graph. There she is. -3, 1 is on the graph. So if that's 4, this is 2, this is 1, 3, -3, 1. There he is. -2, 0 is on the graph. -1, 1 is on the graph. And 0, 4 is on the graph. So here's a pretty solid sketch of that curve. Hopefully you're not surprised by the shape. Right? This is a parabola because the function is a quadratic function. We expect the graph to be a parabola. If you remember anything about the vertex form of a parabola from your previous math classes, this should come as no surprise. But that's not the question I want to ask. The question I want to ask is, what is the simplest function that has the same shape? What is the parent function here?
X squared.
Very good. So I'm going to use g of x for my parent function. And if we compare the graph of x squared with the graph of f here, we know that x squared is also a parabola, looking like this. Okay. I'm trying to draw him in kind of faintly here so it doesn't clutter too badly. You get the idea. Imagine I'm thinking of the blue function as my starting point, because everybody knows what x squared looks like. What would I do to x squared to get f here, x plus 2 squared? What kind of single geometry operation could I do to the blue graph to turn it into the purple graph? Imagine you can pick it up and hold it. What do you do to the blue to make it the purple?
Move it 2 spaces to the left.
Exactly. If this blue graph has some handles on it, I can pick it up and move it 2 to the left and set it down, and that's the purple function. Perfect, perfect, yes, good. So, to obtain the graph of f of x equals x plus 2 squared from the graph of g of x equals x squared, we shift to the left by 2 units. And there is some stuff in the algebra definition of f that tells us this. It's the 2. How do I know to go left or right from the algebra? Well, it's because the 2 is being added on the inside. So if you add 2 to x on the inside, In other words, you replace x by x plus 2. That will shift your graph to the left by 2 units. If you're having trouble with the left or right thing, ask yourself, what x value do I need to plug into this to get 0 out? Well, to get 0 out of this, I need the inside to be 0. How do you get the inside to be 0? You make x negative 2. Negative 2 plus 2 is 0. So the point whose y value is 0 should have x coordinate negative 2. And that's how we know, oh, going to the left. All right, I take every single one of these points, move it to the left 2 units. 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 We all comfy with this guy? All right, let's do one without plotting points. Let's do one just using the transformation rule, which we've discovered. The rules I will write down for you on a list at the end. So don't worry about writing down the rules for now. Just think along with me. I want to sketch the graph of f of x equals 1 over parentheses x minus 3 squared without making a table. So in other words, I want to start with a parent function whose graph I know, and then do something to that graph to get the graph of this guy. What is my parent function?
X squared.
Not quite.
1 over the x squared.
Very good. Yeah, 1 over x squared, or x to the negative 2. Okay. And then what transformation will I apply? What am I going to do to that graph?
We're going to move it 3 to the right.
Very good. 3 units to the right this time, because I've replaced x by x minus 3. So the transformation here is a shift to the right by 3 units. Okay. The graph of the parent function, come down here, give us some nice coordinate axes. The graph of the parent function, 1 over x squared, looks like this. Some points that are on this graph, negative 1, comma 1. Positive 1, comma 1. I feel like you could say negative 2, comma 1/4. I'll just stick with those 2 for now. So if I shift that to the right by 3 units, that vertical asymptote is going to come over. I just drag the blue all the way over here, 3 units. Let me draw it separately. I like to draw in my asymptotes as dotted lines. here is the transformed function. Let me graph a few points. 2, 1, 4, 1. And the graph's going to look like this. Okay. This is the graph f of x equals 1 over x minus 3 squared. You see, it's the same as the blue graph, just moved to the right by 3 units. Questions on this?
Now I can see why we need to remember the parent function so badly.
Yeah, it's a big deal, right? Cooking this up on its own fresh, if you just grab like 4 or 5 random points, maybe you get one up here, maybe you get one over here, maybe you get one over here, and it starts to look like this thing's like, or something weird like that. Really got to have these shapes memorized. Got to know them. What's the best way to learn the graphs of the parent functions? If you haven't done it, going through the process of plotting those using a table will make them stick in your head. At least 1 or 2 from each family, right? You notice they're broken up into families, like the positive integer powers, the roots, and the negative integer powers. Plot 1 or 2 of those by hand, by making a table, and then you'll start to notice the patterns. All right. So yeah, knowing those parent functions is critical. But we've discovered now the whole rule for like horizontal shifting, right? If you subtract a number on the inside, that drags you to the right. And if you add a number on the inside, that drags you to the left. Okay. Let's sketch f of x equals how about the cube root of x plus 1 by plotting points. So we're going to move on to another transformation. We'll start by plotting some points, recognize the rule, and then try an example without plotting points. We're going to do this 3 more times, 1 for each rule. I'm going to make a table. I pretend like I have no idea what else I could do. Maybe we don't. And when you're dead stuck, if you need to graph a function by hand, but you have no idea what else to do, making a table always works. You just need to be careful and patient. Like last time, I chose my x values kind of carefully, -4, -3, -2, -1, 0. I'm going to do the same thing here. This time, I'm going to choose them carefully to make this piece nice. So the cube root of a number isn't nice most of the time. Like the cube root of 2 or 3 or 5, those are all really nasty. But the cube root of 8 is nice. The cube root of 1 is nice. So let's use some nice numbers like -8, -1, 0, 1, and 8. The next perfect cube is 27. So that would require big axes. So I'm going to use just these points. All right. If I plug in -8 for x here, what is the cube root of -8? What number can I multiply by itself 3 times to get -8? 2. Yeah, -2, right? -2 times -2 times -2 is -8. So the cube root of -8 is -2. -2 plus 1 is -1. The cube root of -1, I plug -1 in here is -1. -1 plus 1 is 0. The cube root of 0 is 0. 0 plus 1 is 1. Cube root of 1 is 1. 1 plus 1 is 2. Cube root of 8 is 2. 2 plus 1 is 3. All right, given a little bit of time, I know everybody could come up with this table. So let's plot the graph. Let's graph the function. Let's plot the points. I'll call this -8, which makes this like -4, makes this like -1. Call this +8, which makes this like +4, and makes this like +1. Something like that. And then for my y values, we'll call this -1 down here. We'll call this +1 up here. We'll call this +2, and we'll call this -2. Okay, so -8, -1 is on my graph. There she is. -1, 0 is on my graph. So, -1, 0, yeah. 0, 1 is on my graph. 1, 2 is on my graph, and 8, 3. Ooh, gotta get up here to 3. 8, 3 is on my graph. There he is. So the shape here, maybe you've seen this before, is a kind of funky little sideways looking S-shaped curve. All the odd root functions have graphs that look kind of like these. So here's the graph of f. What do you think would be the parent function for this guy? What part of the cube root of x plus 1 gives us the shape we have here?
X to the power of 1/3.
Yeah, the cube root, right? Just this part. So the parent function, we could say it either way, x to the power of 1/3 or the cube root of x. I'll write it as the cube root because that kind of helps us compare with the guy above. And what does he look like? Well, he goes through 0, 0, 1, 1, -1, -1, 8, 2, and -8, -2. Oh, let me dash him. So what's the relationship between G and F? What's the relationship between the parent and the child? If I started with the blue, how would I get the purple from it? Good. So to obtain the graph of f of x equals the cube root of x plus 1, we, from the graph of g of x equals the cube root of x, we shift vertically up by 1. All right, I take the blue graph and I push everything up by 1 unit. And that will give me the purple graph. Okay. With this in mind, let's sketch function f of x equals x plus 2 all squared minus 4 without making a table. So this new function has elements of both transformation types.
There's going to be x squared, and we have to go 2 to the left and 4 down.
Very good. Yeah, that's it exactly. So the parent function here is g of x equals x squared. And the transformations we're going to do 2 of them. First, we'll shift left by 2 units, then shift down by 4 units. All right, the x plus 2 inside moves me to the left by 2 units. We replace x by x plus 2, that goes left, 2. And then subtracting 4 on the outside, just like adding 1 on the outside moved you up, subtracting 4 on the outside will move you down 4 units. So I'll squeeze this in here. Left and down. Okay, x squared it's like this. Some points that are on that graph, 0, 0, negative 1, 1, and 1, 1. So if I go left 2 units, let me do this one at a time. If I bring this left 1, 2, it lands here. If I bring this guy left 1, 2, it lands here. If I bring this guy left 1, 2, it lands here. So here's the first transformation, just the left shift. And then my last step is to bring everything down by 4. I'll let my cat out here in just a minute, she's being psychotic. So I bring this guy, which is at negative 2, 0, down 4, and he's going to be at negative 2, negative 4. If I bring this guy down 4, he's at negative 3, 1, then he will be at negative 3, negative 3. And if I bring this guy down by 4, right now he's at negative 1, 1, he'll be at negative 1, 3. And this is the graph of the resulting function. This is the final dealio here. All right. If you wanted to sketch just f on its own, just that guy on his own looks like this. The animals are being especially ridiculous this morning. RS this afternoon. All right, so that's it. We went to the left 2, we went down 4, and it turns out order does matter, right? This is the correct order. In this particular case, you could have done it in either order, but I will show you examples where that's not true. So the general idea is you want to do horizontal stuff before vertical stuff. And then within those categories, you always do what are called scalings, which we haven't seen yet, before shifts. I'll be introducing the scaling next, but I want to make sure you're comfy with where this graph comes from. So this is the graph we wanted, right? This is y equals f of x, where f of x is x plus 2 squared minus 4. Okay. Any questions on these last 2 examples? Okay. For my next trick, let's see, we did a cube root, right? Quadratics, done those. Maybe an absolute value. Well, that'll be better for the vertical thing. The roots for these. Tough choice here, tough choice. Let's sketch f of x equals yeah, we can do that. 1 over 2x by plotting points. So it's worth noting here that the domain, it's not all real numbers. X is not allowed to be 0 because that would make the downstairs 0. So you gotta stay away from 0. Let me choose some nice numbers here, like we'll just -2, -1, 1, and 2. If I plug -2 in here, this is 1 divided by 2 times -2, which is -1 over 4. No problem. If I plug -1 in here for x, I'll get 1 over 2 times -1, which is -1/2. If I plug +1 in here, I'll get +1/2. And if I plug +2 in here, I'll get +1/4. So my scales, the scale of the y-axis, I want to be a little mindful of. These are all pretty small numbers. I'll mark this up here as 1, and this down here is -1. And then here's -1, -2, 1, 2, like this. All right, so -2, -1/4. Here's -1. So halfway between the origin and there is -1/2. Halfway between the origin and there is -1/4. So right over here is -2, comma, -1/4. When x is -1, we get -1/2 out. That's right here. -1 comma -1/2. Let's just for fun plug in -1/2 for x and see what we get. That would be 1 divided by 2 times -1/2. Well, 2 times -1/2 is -1. So this would be -1. And similarly, I'll add the symmetric point, the +1/2, comma 1. So those, here's -1/2, comma -1. And then coming over on the other side, we have 1 comma 1/2, 2 comma 1/4. And then we'd have 1/2. The 1/2 comma 1 over here. So what's going on with this graph? Well, it looks a lot like one of our parent functions. It looks a lot like the function 1 over x. So like this. So like I said, the parent function g of x equals 1 over x. And let me add that function in. He goes through 1 comma 1, 2 comma 1/2, 3 comma 1/3. The guy, next guy that would be useful for us here is 4 comma 1/4. And he also goes up like that. So here's the first piece of the parent function. And then on the other side, we'd have -1 comma 1, comma -1, -2 comma -1/2. And then if we go out far enough here to -4, we'd have -4 comma 1/4, which is like that here. So on this side, the parent function looks like this. Can anybody tell what's happened to the blue to get the purple?
The numbers were double small than. But,
if you take your hands, whoop, blocking all the light there. If you take your hands and squish them in like this, you can smush this blue point onto this purple point, this blue point onto this purple point, this blue onto this purple, this blue onto this purple, this blue onto this purple, this blue onto this purple. If you compress the blue function horizontally, it will become the purple function. So to obtain the graph of f of x equals 1 over 2x from the graph g of x equals 1 over x, we're kind of multiplying on the inside by a 2. And what that means is we've got to squish in. The term here is scale horizontally by a factor of 1/2. In other words, you multiply all the x values by 1/2. Take the graph g of x equals 1 over x and multiply all the x values by 1/2. So like here I had the point 2 comma 1/2 on the graph of g. To get the associated point on the graph of f, I multiply by 1/2, and that becomes 1, 1/2. No. Yeah. No. Sit. Lay down. Maxie, I love you. I took you to the park this morning. You had lots of playtime. Daddy's working. Shut the fuck up. So yeah, what Suzanne said in chat is perfect. We've cut things in half horizontally. We've scaled in by 1/2. The term scale is a nice word here. Some people use like stretch or shrink, compress, whatever. But scaling means both of those things. So think about where you've heard the word scale before. Like when someone talks about an economy of scale, they're talking about how things work as you scale up, as you produce more and more, the output or demand might change, right? Become more and more. Or when you're talking about models, right? Like a model of a car, an airplane or something like that. We talk about a 1/10 scale model. That means all the parts on the model are 1/10 the size of the parts on the original. So scaling can mean get bigger or get smaller. What we're doing here is scaling horizontally. So we're getting bigger or smaller in the horizontal by a factor of 1/2. Okay, that means that we're shrinking horizontally by a factor of 1/2 or multiplying all the x values by 1/2. That's how we do it. Okay. So far we have horizontal shifting, vertical shifting, horizontal scaling. There's also a vertical scaling. Let me try another horizontal scaling first. Let's do one without plotting points, without making the table. So let's sketch the graph of f of x equals the square root of negative x without making a table. So what do I just talk? This is a special kind of horizontal scaling, but it's still a horizontal scaling, and all the rules I shared with you work great. What's the parent function? What might be the parent function here? Square root of x, very good. And the transformation is a horizontal scaling, but it's a weird one. By a factor of -1, right? I'm multiplying on the inside, so it's a horizontal scaling. But the thing I'm multiplying by is negative. And that's a little different than what we saw there. But the rule I said, you multiply all the x values on the graph of the original by that number, by the reciprocal of that number, does the job. So let's sketch the graph of the parent function. The square root of x. Let's sum things up here. So 1, 2, 3, 4. Now vertical 1, 2, 3. That's plenty. So the original function, the square root of x, you know what that looks like. Goes through 0, 0, 1, 1, and 4, 2. I should have dashed him, shouldn't I? Sorry. That's the square root of x. That's the parent function. The points here is 0, 0, 1, 1, and 4, 2. If you multiply all of those x values by -1, (4, 2) becomes -4, 2. 1, 1 becomes -1, 1. And 0, 0 stays 0, 0. So here's the graph of the transformed function. Nice big points here. This is a special kind of horizontal scaling called a reflection. It's a horizontal reflection. You're flipping over horizontally. And you could combine this with the other transformations that we've learned about. Like if I had the square root of -2x, then you would flip over and smush in by a factor of 1/2 like that. All right. The last thing we need to meet here is a vertical scaling. And we'll again do it through an example. Let's see. So the question in chat is, can the parent function not be a negative? Why did it switch from a negative to a positive? I want to make sure I understand both sentences there. So the parent function here is regular old square root of x, because he's sort of the simplest function that has this same shape, or if you like, just because he's in the library of parent functions that I gave you. And then why did it switch from a negative to a positive? I'd like to understand that a little better. So what is the it there? Why did what switch from negative to positive? So the parent function is just the square root of x, because he is the simplest function that has the same basic shape as this. Or if you like, he is the only thing from that list that has a 1/2 power. And we know this is a 1/2 power of -x. Yeah, so kind of think of this list of parent functions as being absolute, if you like. Like if anything has a shape like this, then this is the parent function for that guy. If anything has a shape like this, then the 5th root of x is the parent function for that guy. And then this particular transformation happens to be the one that flips him over like that. All right, let's sketch f of x equals 2 times the absolute value of x by plotting points. You know, I see that. He's being difficult this morning, isn't he? Sorry, we've got this puppy in. He's just crazy right now. So here I'll use -2, -1, 0, 1, and 2. If I plug -2 in for x here, then f of -2 is 2 times the absolute value of -2. The absolute value of -2 is 2, so that's 2 times 2, which is 4. If I plug -1 in for x here, this is 2 times the absolute value of -1, which is 2 times 1 is 2. If I plug in 0, then this is 2 times 0, 2 times the absolute value of 0, which is 0. Plug in 1, 2 times the absolute value of 1 is 2 times 1 is 2. Plug in 2, 2 times the absolute value of 2 is 2 times 2 is 4. So this guy looks like this. All right. -2, 4 is on my graph. There she is. -1, 2 is on my graph. There he is. 0, 0 is on my graph. They're there. 1, 2 is over here. And 2, 4 is up here. This is not a parabola. This is dominated by the absolute value. It's like this V-shaped graph. You've probably seen it before. It's not curvy at all. It's just two straight lines. In fact, it's a piecewise function. And we've talked about absolute values as piecewise functions. And you may have guessed from the choice of language there that the parent function here is g of x equals the absolute value of x. And I'm going to add in the parent function here in blue. So 0, 0, and then we would have 1, 1, and -1, 1, -2, 2, and 2, 2. So here comes the parent function. All right, there it is. So what has to be done to the blue to turn it into the purple?
Numbers has to be doubled.
Yeah, the y values on the blue have to be doubled to get the y values on the purple, right? In other words, what we're doing is scaling vertically by a factor of 2. So to obtain the graph for f of x equals 2 times the absolute value of x from g of x equals the regular absolute value of x, we scale vertically by a factor of 2. In other words, we're stretching it out vertically. So if you take the blue graph and you stretch it vertically, scale it vertically, multiply all the y values by 2, that will get you your full graph. And by scale vertically by a factor of 2, what I mean here is multiply all the y values by 2. So there's a difference between the scaling horizontally and the scaling vertically. Scaling horizontally means you multiply all the x values by 1 over that number. Scaling vertically means you multiply all the y values by the number itself. And the way I encourage people to remember the way that it finally clicked for me is just that the horizontal stuff is always kind of the opposite of what you think. Adding on the inside doesn't take you to the right, it takes you to the left. Multiplying on the inside by 5 doesn't multiply all the x values by 5, it multiplies all the x values by 1/5. And then the vertical stuff does exactly what you would think. Okay. What am I doing on time here? Where are we? 1:46. This is 12:30 to 1:45, right? So we're right at time. If you will allow me, I'd like to write down the rules for you so you have them all in one place. Vertical scalings can also be reflections if the number is negative, but these rules are as general and correct as I can be. So transforming graphs. I also mentioned that the order matters, right? We haven't gotten to see a sufficiently complicated example yet today, but I will show you one on Tuesday of next week. So rules for transforming graphs. We always do horizontal scalings first. Then horizontal shifts. Then, if there are any, we do vertical scalings. And then finally, vertical shifts. A horizontal scaling means your function f of x is equal to the parent function of some constant times x. And this scales horizontally, not by c, but by 1 over c, which means you're going to multiply the x values on the parent function by 1 over c. And that works whether c is positive or negative. Horizontal shift, this is where your function, and I'll give you kind of two different versions, is like g of x minus c or g of x plus c. I'm assuming c is positive here. This shifts left by c units, the x minus c, and this guy shifts right by c units. A vertical scaling, that's where your function is equal to some constant times the parent function. And this scales vertically by c. And what that means is we're going to multiply all the y values by c. So you take your parent function and you just multiply all the y values by the constant c, and that will give you the graph of the transfer function. And then a vertical shift.
Sorry, but in second, there's shifts right. I think it's the all the way around. Shifts right. It's vertical.
Oh, I did. Oh my God, what have I done? Good Lord. All right. X minus c. Yeah, I'm so sorry. Thank you. Thank you. You're exactly correct. I'm so sorry. All right. And then finally, vertical shifts. The shift up by c units. The shifts down by c units. All right. So the shifting is fairly intuitive. And the scaling, vertical scalings are fairly intuitive. Horizontal scalings tend to be the tougher of these for people to navigate while they're first meeting them. And then the last thing is, remember to do them in this order. So on Tuesday of next week, we're going to look at some more problems that involve transforming graphs. I am leaning towards publishing another homework set for you guys today that just has some basic transformation questions on it. And then we'll look at some tougher ones on Tuesday. But make sure you focus on getting that quiz done. That quiz is open for you guys, has been for a few days. You want to work on that. And then get a little bit of practice with the transformations. I'll post probably just a small homework set for you guys to work on for this stuff between now and next Tuesday. Then next Tuesday, we'll come back, look at some harder versions where we've got like all of these things that we have to do on a single graph, and you'll see how they interact with each other. If you need to talk to me, I have an office hour tomorrow from 1 to 2 p.m. You can send me a Canvas message or come by the Discord. If you have any troubles, please don't hesitate to reach out for help. In addition to myself, you can ask your fellow classmates in the Discord or talk to the tutors in the Learning Commons. That's it from me, guys. So I hope you have a wonderful rest of your day. And if there's anything I can do to help you, please don't hesitate to ask. Bye.